Okay, I've put in the data points from our dice rolls, 83, 66, 60. This is how many dice were left after removing the ones each time. And you can see how it really forms a nice curve. And it's an exponentially decaying curve, which is the opposite of exponential growth, which would have been rising. So I'm going to show you a couple of things. First of all, let's try to make a line of best fit that goes through these points. So we're going to do a regression model on these. And the standard form for a line is slope-intercept form, y equals mx plus b. If you do that, we can start with this form, change the equal sign to a squiggly line, change the x and y to x sub 1 and y sub 1 with our little underscores, and then Desmos should spit out a regression model for us. Perfect. So what they've just put on top of our graph is the line of best fit through our data, and we can use this line to make predictions. Obviously, you can see it's not actually that good a fit. So we're going to try, instead of using a line, we're going to use our exponential function. The linear function versus exponential function head-to-head. Here's the general form for our exponential function. A is our starting value, B is our growth factor, or what we would multiply the number by each time in order to get to the next point. Remember, if it's doubling, we multiply by 2. And what I'm going to do is change this to a squiggly line, change this to y sub 1, x sub 1, and let's see if this model is a little bit better. Yeah, I would say it's better, wouldn't you? It's almost perfectly tracing our points in our real world data, just based on changing it from a line to an exponential function. And the other thing I want to point out, you see this r squared number? That r squared is basically how good your model is at predicting your points. So the closer it is to 1, the better it is. In our line, it's 0.79, which is pretty high, but not close enough. In our exponential function, our r squared is 0.9939. You can't get much closer to 1 than that. And so you can see that our exponential is almost a perfect fit. The one thing I will want to point out, you see how this a value is 83-ish? That seems to make sense. Our starting value is just about 83. So that's a good sign that our starting value is on track. And our b value is what we would multiply each number by to get to the next. Now, if you think about rolling the dice, each time you shake it, what percent of them are going to come up as 1 dots? 1/6. And 1/6 is just about 16-ish%. So if you take the number 1 and you subtract 16% from it, you'll get this, about 83, 84%. And so this is almost a perfect representation of our actual model, which would have been y equals 83, starting value, times 5/6, or what you would multiply by, to the x power, since you're removing 1/6 each time. And this blue curve and the red curve are almost identical. All right, there you have it, some exponential decay with some real-world data. You saw it first. You saw it right in front of us. I hope you enjoyed it. Go and find some more examples of exponential decay yourself.